Hello everyone, today we'll study logarithmic expressions. First of all, let me introduce logarithm. Let a, x, and y be real numbers with a greater than 0 and a not equal to 1. If a to the power of x is y, then we define log base a of y equal to x. If a to the power of x is y, then we define log base a of y equal to x. This expression, log base a of y equal to x, it means a to the power of x equal to y. This expression, it means a to the power of x equal to y. This x here represents exponent. Note, in the above expressions, y is always positive, since x is positive. If x is a positive number, then positive number raised to any power is always positive. So y is always positive. In these expressions, y is always positive. So if we have log base a of a negative number, if y is negative, log base a of negative number is always undefined, since y cannot be negative. So log base a of a negative number is always undefined. Since y is always positive, so log base a of y of any negative number is undefined. And this expression, log base a of y, is read log base a of y. This expression is read log base a of y. Next, let's do some examples. Evaluate each of the following expressions. First example, how can we evaluate log base 2 of a? How can we evaluate log base 2 of a? This expression, log base 2 of a, is asking 2 raised to what power equal to a. This expression, log base 2 of a, is asking 2 raised to what power is a. 2 raised to what power is a? We know that 2 to the power of 3 is a. So this expression equal to 3. Since 2 to the power of 3 is a, this expression equal to 3. So this number is always an exponent. This number here is always represent exponent. Next example, what's log base 3 of 9? So this expression is asking 3 raised to what power is 9? This expression is asking 3 raised to what power is 9? We know that 3 to the power of 2 is 9. So this expression equal to 2. This expression equal to 2 because 3 to the power of 2 is 9. Next example, log base 5 of 125. Log base 5 of 125. This expression is asking 5 raised to what power is 125? This expression is asking 5 raised to what power is 125? We know that 5 to the power of 3 is 125. So this expression equal to 3. Since 5 to the power of 3 is 125, this expression equal to 3. Next example, log base 10 of 10,000. Log base 10 of 10,000. This expression is asking 10 raised to what power is 10,000? This expression is asking 10 raised to what power is 10,000? We know that 10 to the power of 4 is 10,000. So this expression equal to 4. Next example, what's log base 5 of 1/5? What's log base 5 of 1/5? This expression is asking 5 raised to what power is 1/5? This expression is asking 5 raised to what power is 1/5? 5 raised to what power is 1/5? In general, we call an unknown number x. We're looking for 5 raised to what power is 1/5? We know that 1/5 can be written as 5 to the power of -1. Then, by matching the left side and right side, we have x equal to -1. That means 5 to the power of -1 is 1/5. That means 5 to the power of -1 is 1/5. Next example. What's log base 7 of 1/49? What's log base 7 of 1/49? This expression is asking 7 raised to what power is 1/49? This expression is asking 7 raised to what power is 1/49? 7 raised to what power is 1/49? We know that 1/49 can be rewritten as 1/7 squared, because 49 is 7 squared. And then 1/7 squared can be rewritten as 7 raised to -2. 1/7 squared can be rewritten as 7 raised to -2. Then, by matching left side and right side, we have x equal to 2. If we match the left side and right side, you can see that x equal to -2, which means 7 to the power of -2 is 1/49. That means 7 to the power of -2 is 1/49. So that's an answer to this expression. Next example. Log base 2 of 1/32. What's log base 2 of 1/32? This expression is asking 2 raised to what power equal to 1/32? This expression is asking 2 raised to what power is 1/32? We know that 1/32 can be rewritten as 1/2 to the power of 5. 32 is 2 to the power of 5. And then 1/2 to the power of 5 can be rewritten as 2 to the power of -5. Then, by matching the left side and right side, you can see that x must be -5. So the answer is -5. That means 2 to the power of -5 is 1/32. That means 2 to the power of -5 is 1/32. Next example. Log base 10 of 1/1000. Log base 10 of 1/1000. This expression is asking 10 raised to what power is 1/1000? 10 raised to what power is 1/1000? Let's run the equation first. So this problem is asking 10 raised to what power is 1/1000? We know that 1/1000 can be rewritten as 1/10 to the power of 3. 1000 is 10 to the power of 3. Then 1/10 to the power of 3 can be rewritten as 10 to the power of -3. Then, by matching the left side and right side, you can see that x equal to -3. By matching the left side and right side, you can see that x equal to -3. So the answer is -3. That means 10 to the power of -3 is 1/1000. Next example. What's log base 5 of square root of 5? What's log base 5 of square root of 5? So this expression is asking 5 raised to what power is square root of 5? This expression is asking 5 raised to what power is square root of 5? And we know that square root of 5 can be rewritten as 5 to the power of half. Then, by matching the left side and right side, you can see that s equal to a half. That means the answer is half. This answer half, it means 5 to the power of half is square root of 5. This answer, it means 5 to the power of half equal to square root of 5. Next example. What's log base 11 of cube root of 11? What's log base 11 of cube root of 11? So this expression is asking 11 raised to what power is cube root of 11? this expression is asking 11 raised to what power is cube root of 11? We know that cube root of 11 can be rewritten as 11 to the power of 1/3. Then, by matching the left side and right side, you can see that x is equal to 1/3. So the answer for this expression is 1/3. It means 11 to the power of 1/3 is cube root of 11. Next example. What's log base 3 of the fifth root of 9? What's log base 3 of the fifth root of 9? So this expression is asking 3 raised to what power is the fifth root of 9? This expression is asking 3 raised to what power is fifth root of 9? Let's simplify fifth root of 9 first. 9 can be rewritten as 3 squared. Then we have fifth root of 3 squared. Fifth root of 3 squared can be rewritten as 3 to the power of 2/5. The exponent is the numerator. The index is the denominator. So the fifth root of 3 squared can be written as 3 to the power of 2/5. Exponent is the index. Exponent is the numerator. Index is the denominator. Then, by matching the left side and right side, you can see that x equal to 2/5. By matching the left side and right side, you can see that x equal to 2/5. So the answer is 2/5. That means 3 to the power of 2/5 is the fifth root of 9. This expression means 3 to the power of 2/5 equal to the fifth root of 9. Next example. How do we evaluate log base 2 of cube root of 32? What's log base 2 of cube root of 32? So this expression is asking 2 raised to what power is cube root of 32? This expression is asking 2 raised to what power is cube root of 32? Let's simplify cube root of 32 first. We know that 32 is 2 to the power of 5. 32 is 2 to the power of 5. And 2, the cube root of 2 to the power of 5 can be rewritten as 2 to the power of 5/3. Cube root of 2 to the power of 5 can be rewritten as 2 to the power of 5/3. Exponent is the numerator. Index is the denominator. Base 2 stays the same. Then, by matching the left side and right side, you can see that x equal to 5/3. X equal to 5/3. So the answer is 5/3. This answer means 2 to the power of 5/3 is cube root of 32. This answer means 2 to the power of 5/3 is cube root of 32. Next example. How can we evaluate log base 9 of 27? What's log base 9 of 27? So that's not easy. 9 raised to what power is 27? That's not easy. Let's set an equation first. So this problem is asking 9 raised to what power is 27? We're looking for exponent here. 9 raised to what power is 27? Let's simplify left side and right side. On the left side, 9 can be rewritten as 3 squared. X stays the same. 9 can be rewritten as 3 squared. 27 can be rewritten as 3 to the power of 3. 27 can be rewritten as 3 to the power of 3. Then, by matching the left side and right side, we can see that the base is exactly the same, which means the exponent must also be the same. So the exponent 2x equal to 3. If the base is the same, exponent must also be the same. So we get 2x equal to 3. Then, in order to isolate x, I can divide both sides by 2. I get s equal to 3 over 2. Here we get s equal to 3 over 2. That means the answer here is 3 over 2. This answer means 9 to the power of 3 over 2 is 27. This answer means 9 to the power of 3 over 2 is 27. We can check. 9 to the power of 3 over 2 is, this can be rewritten as the second root of 9 to the power of 3. The denominator is the index. Numerator is exponent. And we know that the second root is the same as square root. Square root of 9 is 3. 3 to the power of 3 is 27. So 9 to the power of 3 over 2 is 27. That's an answer to this logarithm. Next example. What's log base 25 of 5? What's log base 25 of 5? What's log base 25 of 5? This expression is asking 25 raised to what power is 5? This expression is asking 25 raised to what power is 5? We know that 25 can be rewritten as 5 squared. X stays the same. And 5 by itself is 5 to the power of 1. 5 by itself is the same as 5 to the power of 1. Then, match the left side and right side. We can see that the base is exactly the same. That means the exponent must also be the same. So we have 2x equal to 1. Then, in order to solve for x, I can divide both sides by 2. I get s equal to half. So the answer is half. That means 25 to the power of half is 5. That means 25 to the power of half is 5. Let's check. 25 to the power of half is the same as square root of 25. And square root of 25 is 5. So 25 to the power of half is 5. The answer for this logarithmic expression is a half. Next example. What's log base 16 of a? What's log base 16 of a? So let's set down the equation first. This expression is asking 16 raised to what power is a? This expression is asking 16 raised to what power is a? How can we get x by itself here? On the left side, 16 can be rewritten as 2 to the power of 4. X stays the same. On the right side, a can be rewritten as 2 to the power of 3. Then, by matching the left side and right side, we can see that if the base is the same, the exponent must be the same. So we have 4x equal to 3. Then I can divide both sides by 4. If I divide both sides by 4, I get s equal to 3 over 4. So the answer is 3 over 4. That means 16 to the power of 3 over 4 is a. That means 16 to the power of 4, 16 to the power of 3 over 4 is a. We can check the answer here. 16 to the power of 3 over 4. That can be rewritten as the 4 root of 16 to the power of 3. The denominator is the index. Numerator is exponent. For any rational exponents, denominator is the index. Numerator is the exponent outside. And we know that the 4 root of 16 is 2. 2 to the power of 3 is a. That means 16 to the power of 4 over 3 is a. So 16 to the power of 3 over 4 is a. That's an answer for this logarithmic expression. Next example. What's log base a of 32? What's log base a of 32? This expression is asking a raised to what power is 32? This expression is asking a raised to what power is 32? So let's set out the equation first. This expression is asking a raised to what power is 32? Let's rewrite the left side and right side first. On the left side, number a can be rewritten as 2 to the power of 3. X stays the same in the exponent. On the right side, 32 is 2 to the power of 5. Then, by matching the left side and right side, we can see that their base is exactly the same. If the base is the same, the exponent must also be the same. So we have 3x equal to 5. Next, I can divide both sides by 3, get s by itself. S equal to 5 over 3. So the answer is 5 over 3. That means a to the power of 5 over 3 is 32. That means a to the power of 5 over 3 is 32. We can check. A to the power of 5 over 3. For this rational exponent, it can be rewritten as cube root of a to the power of 5. For any rational exponents, the denominator is the index, numerator is exponent. Then do the parentheses first. Cube root of a is 2. 2 to the power of 5 is 32. That means a to the power of 5 over 3 is 32. So a to the power of 5 over 3 is 32. That's an answer for this logarithmic expression. Next example. What's log base square root of 5 of 1 over 25? How to evaluate log base square root of 5 of 1 over 25? This expression is asking square root of 5 raised to what power is 1 over 25? This expression is asking square root of 5 raised to what power is 1 over 25? So let's set out the equation first. This expression is asking square root of 5 raised to what power is 1 over 25? We know that square root of 5 can be rewritten as 5 to the power of 1 over 2. X stays the same exponent. And 1 over 25 is 1 over 5 squared. 25 can be rewritten as 5 squared. Then, let me keep left side the same. Half times x is x over 2. Half times x is x over 2. For the right side, 1 over 5 squared can be rewritten as 5 to the power of negative 2. On the right side here, 1 over 5 squared can be rewritten as 5 to the power of negative 2. And then, by matching the left side and right side, you can see that x over 2 equal to negative 2. Since the exponent, the base is the same, the exponent must equal to each other. So s over 2 equal to negative 2. Next, we try to get s by itself. Here, in order to get s by itself, I can multiply both sides by 2. If I multiply both sides by 2, I get s equal to negative 4. So the answer is negative 4. That means negative 5 to the power of negative 4. Radical 5 to the power of negative 4 is 1 over 25. That means radical 5 to the power of negative 4 is 1 over 25. You can try the answer by yourself. Next example. What's log base radical 27 of 1 over radical 3? What's log base radical 27 of 1 over radical 3? So this expression is asking radical 27 raised to what power is 1 over radical 3? This expression is asking radical 27 raised to what power is 1 over radical 3? Radical 27 raised to what power is 1 over radical 3? So let's rewrite left side and right side first. On the left side here, square root of 27. 27 can be rewritten as 3 to the power of 3. 27 can be rewritten as 3 to the power of 3. On the right side, square root of 3 is the same as 3 to the power of a half. Square root of 3 is 3 to the power of a half. Next, let me rewrite the left side here. Left side we have square root of 3 to the power of 3. So base is 3. The exponent is 3. For square root, we assume the index is 2. So we get 3 over 2. For square root, we assume the index is 2. So we get 3 over 2. Exponent is the numerator. Index is the denominator. And then x stays the same in the exponent. On the right side, 1 over 3 to the power of a half is 3 raised to negative half. Then, by matching the left side and right side, we can see that their base is exactly the same. If the base is exactly the same, the exponent must also be the same, which means 3 over 2x must equal to negative 1 over 2. So 3 over 2 times x must be the same as negative 1 over 2. Then solve the equation for x. Solve the equation for x. Here we can see that they have common denominator 2. So I can multiply both sides by 2. If I multiply left side by 2, I get 3x. If I multiply right side by 2, I get negative 1. Then, in order to get s by itself, I can divide both sides by 3. S equal to negative 1/3. Which means the answer for this logarithmic expression is negative 1/3. The answer for this logarithmic expression is negative 1/3. This answer means radical 27 to the power of negative 1/3 is 1 over radical 3. Next example, log base 1 over a of cube root of 4. How can we evaluate this logarithmic expression? This expression is asking 1 over a raised to what power is cube root of 4. This expression is asking 1 over a raised to what power is cube root of 4. So let me write down the equation first. This expression is asking 1 over a raised to what power is cube root of 4. So let's simplify the left side and right side. On the left side, 1 over a can be rewritten as 1 over 2 to the power of 3. Because number a can be written as 2 to the power of 3. On the right side, number 4 can be rewritten as 2 squared. Number 4 can be rewritten as 2 squared. Then, if we simplify left side, 1 over 2 to the power of 3, that can be rewritten as 2 to the power of negative 3. 1 over 2 to the power of 3, that can be rewritten as 2 to the power of negative 3. And x is exponent, it stays the same in the exponent. On the right side, cube root of 2 squared can be rewritten as 2 to the power of 2/3. Cube root of 2 squared can be rewritten as 2 to the power of 2/3. The exponent becomes numerator. Index in the front becomes denominator. Then, match the left side and right side. We can see that they have the same base. So the exponent must be exactly the same. We get negative 3x equal to 2 over 3. Next, we try to get s by itself. How can I get s by itself here? I can divide both sides by negative 3. I can divide both sides by negative 3. So s equal to 2/3 divided by negative 3. For 2/3 divided by negative 3, I can rewrite negative 3 as negative 3 over 1. When we have a fraction divided by a fraction, we keep the top fraction the same. Flip the bottom fraction over. Then multiply, we get 2 over negative 9. Keep the top fraction the same. Flip the bottom fraction over. Multiply 3 across. We get 2 over negative 9, which is the same as negative 2 over 9. 2 over negative 9 is the same as negative 2 over 9. So that's an answer for this logarithmic expression. Negative 2 over 9. That means 1 over a to the power of negative 2 over 9 is cube root of 4. Next example. How can we evaluate log base of 1 over 9? Log base 1 over 9 of 1 over the 4 root of 27. How can we evaluate this logarithmic expression? Log base 1 over 9 of 1 over the 4 root of 27. This expression is asking 1 over 9 raised to what power? 1 over 9 raised to what power equal to 1 over the 4 root of 27. Let me rewrite both sides first. Let me simplify both sides first. On the left side, 1 over 9 can be rewritten as 1 over 3 squared. 9 is 3 squared. On the right side, 1 over the 4 root of 27 can be rewritten as 1 over the 4 root of 3 to the power of 3. 27 is 3 to the power of 3. Then, on the left side, 1 over 3 squared can be rewritten as 3 to the power of negative 2. 1 over 3 squared can be rewritten as 3 to the power of negative 2. And x stays the same as in the exponent. This x stays the same in the exponent. On the right side, the 4 root of 3 cubed is 3 to the power of 3 over 4. The 4 root of 3 cubed is 3 to the power of 3 over 4. Exponent is the numerator. Index is the denominator. Next, let me rewrite right side. 1 over 3 to the power of 3 over 4. Next, 3 to the power of negative 3 over 4. Then, match the left side and right side. We can see that the base is exactly the same. If the base is the same, the exponent must also be the same. So, negative 2x equal to negative 3 over 4. Next, we try to get s by itself. In order to get s by itself, I divide both sides by negative 2. So s equal to negative 3 over 4 divided by negative 2. Negative 2 can be rewritten as negative 2 over 1. When we have a fraction divided by another fraction, we keep the top fraction the same. Flip the bottom fraction over. Again, negative 2 over 1. Negative 1 over 2. Keep the top fraction the same. Flip the bottom fraction over. Then multiply 3 across. When we multiply, double negative becomes positive. We get 3 over a. So x is 3 over a. That's the answer of this logarithmic expression. Answer is 3 over a. This answer means 1 over 9 to the power of 3 over a is 1 over the 4 root of 27. That's what this answer means. Next, let me show you some properties of logarithms. First property, log base a of 1 is 0, because a to the power of 0 is 1. Because a to the power of 0 is 1. Second property, log base a of a is 1, because a to the power of 1 is a. Log base a of a is 1, because a to the power of 1 is a. Next property, log base a of a to the power of x is x. Log base a of a to the power of x is x, because a to the power of x is a to the power of x. Because a to the power of x is a to the power of x. So log base a of a to the power of x equal to x. Next property, a to the power of log base a of x equal to x. A to the power of log base a of x equal to x. Why is that? Keep in mind, this expression, log base a of x, it represents an exponent such that this represents exponent such that a raised to this exponent is x. So log base a of x, this expression represents exponent such that a raised to this exponent equal to x. This expression represents exponent such that a raised to this exponent equal to x. So for example, log base 2 of a, this expression represents exponent. Here we know the exponent is 3 here. That means 2 raised to this exponent is a. This expression represents exponent such that 2 raised to this exponent is a. So this expression log base a of x represents exponent such that a raised to this exponent is x. So a raised to this exponent is x. So keep these 4 properties in mind. Log base a of 1 is 0. Log base a of a is 1. Log base a of a to the power of x is x. And the fourth one, a to the power of log base a of x is x. If these two bases they are exactly the same, a cancels log a, I get s by itself. If these two bases looks exactly the same, a cancels log a, I get s by itself. Next, let me show you the law of logarithms. Let me show you the law of logarithms. First law says log base a of x times y is log base a of x plus log base a of y. Log base a of x times y equal to log base a of x plus log base a of y. Why is that? How is that true? So let's prove it. For the first law here, I first of all let log base a of x equal to u, and let log base a of y equal to v. Let log base a of x equal to u, and let log base a of y equal to v. Then log base a of x equal to u, that means a to the power of u equal to x. And log base a of y equal to v, that means a to the power of v equal to y. We have log base a of sy, log base a of sy, that can be rewritten as log base a of x is a to the power of u, y is a to the power of v. Then, by the law of exponents, a to the power of u times a to the power of v, that can be rewritten as log base a of a to the power of u plus v. By the law of exponents, by rule of exponents, a to the power of u times a to the power of v, that's the same as a to the power of u plus v. And then, by the third property of logarithm, log base a of a to the power of x is x. So log base a cancels a, we get s by itself. Log base a cancels a, we get u plus v. By the third law of logarithm, by the third property of logarithm here, log base a of a to the power of x is equal to x. That means log base a cancels a. Log base a cancels a, I get u plus v by itself. Then we know that u is log base a of x, and v is log base a of y. So log base a of x times y is log base a of x plus log base a of y. That's the proof for the first law. For the second law, log base a of x over y is log base a of x minus log base a of y. Log base a of x over y is log base a of x minus log base a of y. How can we prove it? Very similar. Proof is very similar. First of all, do the same thing. Let log base a of x equal to u, and let log base a of y equal to v. Then a to the power of u equal to x, and a to the power of v equal to y. We have log base a of x over y. Log base a of x over y can be rewritten as log base a of a to the power of u over a to the power of v. Here x is a to the power of u, y is a to the power of v. Substitute. Then by the rule of exponents, a to the power of u over a to the power of v, that can be rewritten as a to the power of u minus v. A to the power of u over a to the power of v can be rewritten as a to the power of u minus v. Then, by the third property of logarithm, log base a of a to the power of x equal to x. That means log base a of a get cancelled. What's left is x. So, log base a of a get cancelled. What's left is u minus v. And we know that u is log base a of x. U is log base a of x. V is log base a of y. So that's the proof of the second law of logarithm. Log base a of x over y is log base of x minus log base a of y. That's the second law of logarithm. Next, the third law of logarithm says log base a of x to the power of r can be rewritten as r times log base a of x, which means I can bring exponent to the front. When x has an exponent, I can bring exponent to the front of log. So log base a of x to the power of r can be rewritten as r times log base a of x. Let's prove it. So for the third property, do the same thing. I let log base a of x equal to u. Let log base a of x equal to u. Then that means a to the power of u equal to x. What we have here is log base a of x to the power of r. What we have here is log base a of x to the power of r. And we know that x is a to the power of u. X is a to the power of u. This x is a to the power of u to the power of r. Then by the law of exponent, when we have a to the power of u to the power of r, that can be rewritten as a to the power of u r. When we have a to the power of u to the power of r, that can be rewritten as a to the power of u r. Then by the third property of logarithms, log base a of x is x. I can cancel log base a of a. Here I can cancel log base a of a. I get u times r. And here r, let me leave it in the front. Let me write r in the front. U is log base a of x. This u is log base a of x. So that's the third law. Log base a of x to the power r is r times log base a of x, which means I can bring exponent r to the front. That's the third law of logarithm. Log base a of x to the power r is r times log base a of x. Next, let me show you the change of base formula. Change of base formula says log base a of b equal to log base c of b over log base c of a. for all real numbers c. This formula works for all real numbers c greater than 0. C must be greater than 0, and c cannot be 1. This formula works for all real numbers c. C must be greater than 0, and c cannot be 1. That's called a change of base formula. With this formula, we can change the base from a to c. With this formula, I can change the base from a to c. Since c can be any real number, so I can change the base from a to any real numbers. Next, let's prove it. In order to prove this formula, I first of all let log base c of b, then the numerator log base c of b equal to u, then the denominator log base c of a equal to v, and then the right side here log base a of b equal to w. So let the numerator be u, denominator be v, and then the left side be w. Then next I can rewrite each log. First log base c of b equal to u can be rewritten as c to the power of u equal to b. Second log base c of a equal to v, that can be rewritten as c to the power of v equal to a. Next formula, log base a of b equal to w, that can be rewritten as a to the power of w equal to b. A to the power of w equal to b. Next, I can replace this a with c to the power of v. I can replace this b with c to the power of v, c to the power of u. So I can replace a with c to the power of v, replace b with c to the power of u, then simplify the left side. By the law of exponent, c to the power of u to the power of v can be rewritten as c to the power of uv of vw equal to c to the power of u. Then match the left side and right side, we can see that if the base is the same, their exponent must be the same. So v times w equal to u. V times w equal to u. From this formula, I have w equal to u over v. From this formula, I can get w by itself. W equal to u over v, I can divide both sides by v. W equal to u over v, and we know that w is log base a of b. W is log base a of b. U is log base c of b. And v is log base c of a. So that's the proof of this formula. Log base a of b equal to log base c of b over log base c of a for all real numbers c greater than 0 and c not equal to 1. With this formula, I can change the base from a to c, and c can be any real numbers. So I can change the base from a to any real numbers. This is called the change base formula. So keep these properties, these laws, and this formula in mind. Next, let's do some examples. Simplify each of the following expressions. First example, how can we simplify 3 to the power of log 3 of 7? We know that one of the property of logarithm says a to the power of log base a of x equal to x, which means if the base is the same, a will cancel log base a. What's left is x. So keep this formula in mind. We know that a to the power of log base a of x equal to x. Here we have 3 to the power of log base 3 of 7. If the base is the same, 3 cancels log 3. What's left is 7. That's an answer. That's a simplified answer for this expression. Next example. How can we simplify 5 to the power of log base 5 of a? Here, since the base is the same, 5 to the power of log 5 of a equal to a. Number 5 cancels log 5. I get a by itself. A always cancel log base a. What's left is x. So that's the simplified answer for this expression. Next example. How can we simplify 2 to the power of log base 2 of 9? Since the base is the same, 2 will cancel log base 2. What's left is number 9. Next example. How can we simplify 7 to the power of log base 7 of 6? Since base 7 is the same, 7 will cancel log base 7. What's left is number 6. Next, how can we simplify 9 to the power of log base 3 of 11? How can we simplify 9 to the power of log base 3 of 11? Now the base looks different. What can we do here? Now the base looks a little different. What can we do here? So let's try to make the base the same. Let's try to make the base the same. Number 9 can be rewritten as 3 squared. And this 2 is part of exponent. This log is also part of exponent. Write exponent together, I get 2 times log base 3 of 11. 9 is 3 squared. This 2 is part of exponent. And this log is also part of exponent. So put exponent together, I get 2 times log base 3 of 11. Now, how can we simplify this? There's extra 2 here. What can we do? We know that if we have a to the power of log base a, they can cancel. We have 2 here. What can we do? So, in exponent, 2 times log base 3 to the power of 11, that can be rewritten as 3 to the power of log base 3 of 11 times 2. I can switch order. Write log in the front, 2 on the back. Then, by the law of exponent, we know that a to the power of x to the power of y can be rewritten as a to the power of sy, which means a to the power of sy can be rewritten as a to the power of x first, and then raised to the power of y. So this expression can be rewritten as 3 to the power of log base 3 of 11 raised to the power of 2. I can separate the exponent. Then inside the parentheses, 3 to the power of log base 3 of 11. If the base is the same, 3 cancels log 3, I get 11 by itself. So I get 11 to the power of 2. And we know that 11 to the power of 2 is 121. So that's the simplified expression. That's the simplified expression for this. Next example. How can we simplify a to the power of log base 2 of 5? Here the base is different. So we try to make the base the same. Number a can be rewritten as 2 to the power of 3. And 3 is part of exponent. This log is also part of exponent. So I write 3 times log base 2 of 5. We multiply exponent together. Then this exponent can be rewritten as 2 to the power of log base 2 of 5 times 3. We try to put 2 to the power of log base 2 of 5 together. So this can be rewritten as 2 to the power of log base 2 of 5 to the power of 3. And then inside the parentheses, we have 2 to the power of log base 2 of 5. If the base is the same, they can cancel. What's left is number 5. So what's left is 5 to the power of 3. And we know that 5 to the power of 3 is 125. That's how we simplify this expression. The answer is 125. Next example. How can we simplify? Square root of 5 to the power of log base 5 of 3. How can we simplify? Square root of 5 to the power of log base 5 of 3. Here you can see that the base is different. In order to use this formula, we try to make the base the same. Here, square root of 5 can be rewritten as 5 to the power of 1 over 2. 1 over 2 is part of exponent, and this logarithm is also part of exponent. So you get half times log base 5 of 3. Next, I can switch order, put half on the back. I get 5 to the power of log base 5 of 3 times half. Then, by the law of exponent, this can be rewritten as 5 to the power of log base 5 of 3 to the power of half. Then here, inside the parentheses, we have 5 to the power of log 5 of 3. The base is exactly the same. When the base is the same, I can cancel 5 and log 5. What's left is number 3. And power half stays the same. 3 to the power of half is square root of 3. That's how we simplify this expression. So the simplified answer is square root of 3. Next example. How can we simplify cube root of 7 to the power of log base 7 of a? How can we simplify cube root of 7 to the power of log base 7 of a? Here we can see that the base looks different. In order to use this formula, we try to make the base the same. Cube root of 7 can be rewritten as 7 to the power of 1 over 3. 1 over 3 is part of exponent, and this logarithm is also part of exponent. So we have 1 over 3 times log base 7 of a. Next, I can move 1/3 from the back. I get 7 to the power of log base 7 of a times 1/3. Then, by the law of exponent, this can be rewritten as 7 to the power of log base 7 of a to the power of 1/3. And then inside the parentheses, we have 7 to the power of log base 7 of a. If the base is the same, 7 will cancel log base 7. What's left is number a. So I get a to the power of 1/3. A to the power of 1/3 can be rewritten as cube root of a. And we know that cube root of a is 2. So that's the simplified answer. That's the simplified answer for this expression. Next, let me show you some different examples. Expand each of the following expressions. First example, log base 2 of 16 times a to the power of 5 times b to the power of 4. How can we expand this expression? In order to expand a logarithmic expression, we need to apply the law of logarithms. We need to use these 3 laws of logarithms to expand a logarithmic expression. So, first step, we can convert multiplication to addition. By the first law of logarithm, we can convert multiplication to addition. So, this logarithm can be written as log base 2 of 16 plus log base 2 of a to the power of 5 plus log base 2 of b to the power of 4. By the first law of logarithm, we can convert multiplication to addition. Then simplify each of them individually. For the first term, log base 2 of 16, we can evaluate this manually. For log base 2 of 16, we know that 2 to the power 4 is 16. So log base 2 of 16 is 4. Since 2 to the power 4 is 16, so log base 2 of 16 is 4. For the second term, we have log base 2 of 8 to the power of 5. By the third law of logarithm, if there's exponent here, I can bring exponent to the front. If there's exponent, I can bring exponent to the front. I get 5 times log base 2 of a. And for the last term here, if there's exponent, I can bring exponent to the front. By the third law of logarithm, I get 4 times log base 2 of 4, log base 2 of b. That's the final answer. Here I span this logarithm into these 3 terms. Next example, expand log base 3 of 27 times x to the power of 3, y to the power of 2 times z. So by the first law of logarithm, when we have a multiplication, I can convert to addition. So this can be rewritten as log base 3 of 27 plus log base 3 of x cubed plus log base 3 of y squared plus log base 3 of z. Then simplify each term individually. For the first term, log base 3 of 27, we know that 3 to the power 3 is 27. That means log base 3 of 27 is 3. Because 3 to the power 3 is 27. That means log base 3 of 27 is 3. For the second term, we have log base 3 of x cubed. If there's exponent here, by the third law of logarithm, I can bring exponent to the front. I get 3 log base 3 of x. Next term, I get log base 3 of y squared. By the third law of logarithm, I can bring exponent to the front. I get 2 log base 3 of y. For the last term, if there's no exponent, I leave it the way it is. I get log base 3 of z. That's how I expand this logarithm. Next example. Log base 5 of 25 times x cubed over y to the power of 7. Now, we have log base 5 of 25 x cubed over y to the power of 7. When we have division here, by the second law of logarithm, we can convert division to subtraction. When we have log base a of s over y, I can convert division to subtraction. So when we have division by the second law of logarithm, this can be rewritten as log base 5 of 25 x cubed minus log base 5 of y to the power of 7. Then, in the first logarithm, we have multiplication here. In the first logarithm, we have multiplication. By the first law of logarithm, I can convert multiplication to addition. I get log base 5 of 25 plus log base 5 of x cubed. Keeping the last term the same. Minus log base 5 of y to the power of 7. Then simplify each term individually. For the first term, log base 5 of 25, we know that 5 to the power of 2 is 25. That means log base 5 of 25 is 2. For the second term, if there's exponent, then by the third law of logarithm, we can bring exponent to the front. I get 3 log base 5 of x. And for the last term, if there's exponent here, I can bring exponent to the front. I get 7 log base 5 of y. Next example, expand log base 7 of a to the power 4 or times b to the power 3 over 49 times c squared. For any logarithmic expression, if there's division, we can convert division to subtraction by the second law of logarithm. So this expression can be rewritten as log base 7 of a to the power of 4 times b to the power of 3 minus log base 7 of 49c squared. So I first of all convert division to subtraction. Next, we can convert multiplication to addition. We have a to the power of 4 times b to the power of 3. 49 times c squared. We can convert multiplication to addition. So the first term can be rewritten as log base 7 of a to the power of 4 plus log base 7 of b to the power of 3. The second term can be rewritten as log base 7 of 49 plus log base 7 of c squared. Next, if there's exponent, I can bring exponent to the front. So I have 4 log base 7 of a plus 3 log base 7 of b minus log base 7 of 49. Since 7 squared is 49, that means log base 7 of 49 is 2. Since 7 to the power 2 is 49, log base 7 of 49 is 2. Distribute negative sign. The last term becomes negative. Then I can bring 2 to the front. I get 2 log base 7 of c. That's how I expand this expression. Next example. Log base 11 of radical a times b to the power of 4. Log base 11 of radical a times b to the power of 4. So for logarithm, we can convert multiplication to addition. By the first law of logarithm, I can convert multiplication to addition. So I have log base 11 of radical a plus log base 11 of b to the power of 4. And we know that radical a is the same as a to the power of 1 over 2. Radical a is the same as a to the power of 1 over 2. By the third law of logarithm, we can bring exponent to the front. So I get 1 over 2 log base 11 of a plus 4 times log base 11 of b. By the third law of logarithm, we can bring exponent to the front. Next example. Expand log base 13 of x over cube root of y. Expand log base 13 of x over cube root of y. So here we have division here. By the second law of logarithm, we can convert division to subtraction. So we get log base 13 of x minus log base 13 of cube root of y. And we know that cube root of y is the same as y to the power of 1/3. Then by the third law of logarithm, we can bring exponent to the front. In the first term, there's no exponent, so I leave it the way it is. I get log base 13 of x minus, here bring 1/3 to the front. I get 1/3 log base 13 of y. Next example. Expand log base 9 of radical 3x cubed over y squared. Expand log base 9 of radical 3x cubed over y squared. So we have division here. By the second law of logarithm, we can convert division to subtraction. So this expression can be rewritten as log base 9 of radical 3x cubed minus log base 9 of y squared. Now, radical 3x cubed, it can be rewritten as 3x cubed raised to a half. Radical 3x cubed can be rewritten as 3x cubed raised to a half. If there's exponent, I can bring exponent to the front. So I get a half log base 9 of 3x cubed. I bring exponent to the front. I get half log base 9 of 3x cubed minus, here bring 2 power 2 to the front, I get minus 2 log base 9 of y. Now, in the first term, we have multiplication. I can convert multiplication to addition. By the first law of logarithm, I can convert multiplication to addition. So I get half log base 9 of 3 plus log base 9 of x cubed minus 2 log base 9 of y. I convert multiplication to addition. Half stays in the front. I get log base 9 of 3 plus log base 9 of x cubed. Then simplify each term individually. For the first term, log base 9 of 3. Log base 9 of 3 equal to what? This expression is asking 9 raised to what power is 3? 9 raised to what power is 3? We know that 9 can be rewritten as 3 squared. And x stays here in exponent. 3 by itself is 3 to the power of 1. Since the base is the same, exponent must be the same. So 2s equal to 1. Divide both sides by 2, s is half. So log base 9 of 3 is a half. Log base 9 of 3 is half. That means 9 to the power of half is 3. So the first term is half. For the second term, I can bring 3 to the front. If there's exponent, I can bring 3 to the front. I get 3 log base 9 of x minus 2 log base 9 of y. Then, for the final answer, distribute half. I get 1 over 4 plus 3 over 2 log base 9 of x minus 2 log base 9 of y. Next example, expand log base a of cube root of 2a squared b to the power of 4. Expand log base a of cube root of 2a squared b to the power of 4. So first of all, we have exponent here. Cube root of 2a squared b to the power of 4 can be rewritten as 2a squared b to the power of 4 raised to 1/3. Okay, we can consider the cube root is the power of 1 over 3. Then, by the third law of logarithm, we can bring exponent to the front. I get 1/3 of log base a of 2a squared b to the power of 4. The cube root is the same as the power of 1 over 3. Here I bring 1 over 3 to the front. What's left is 2a squared b to the power of 4. Next, by the first law of logarithm, we can convert multiplication to addition. So I get log base a of 2 plus log base a of a squared plus log base a of b to the power of 4. Then simplify each term individually. For the first term, we have log base a of 2. Log base a of 2 is asking a raised to what power equal to 2. Log base a of 2 is asking a raised to what power is 2. A raised to what power is 2. We know that number a can be rewritten as 2 to the power of 3. X is part of exponent. I leave it here in exponent. Number 2 by itself can be written as 2 to the power of 1. Now match the left side and right side. Since the base is the same, the exponent must be the same. I get 3x equal to 1. Next, I can divide both sides by 3. I get s equal to 1/3. That means a to the power of 1/3 is 2. So the answer is 1/3. Plus, if there's exponent, I can bring exponent to the front. By the third law of logarithm, I can bring exponent to the front. I get 2 log base a of a. And in the last term, if there's exponent, I can bring exponent to the front. I get 4 log base a of b. And then for the final answer, distribute 1/3. Distribute 1/3. I get 1/9 plus 2/3 log base a of a plus 4/3 log base a of b. That's how we expand this expression. Next, let me show you some different examples. Combine each of the following expressions into a single logarithm. First example, we have 2 log base 2 of x plus 4 log base 2 of y. We should combine this expression into a single logarithm. So, first step, if there's a coefficient in the form, by the third law of logarithm, we try to work backward. If there's a coefficient in the form, I can put it back as exponent. If there's a coefficient in the form, I can put it back as exponent. So first step, we put 2 back as exponent here, and put 4 back as exponent here. I get log base 2 of x squared plus log base 2 of y to the power of 4. Next, we have addition. Then, by the first law of logarithm, if I work backward, I can convert addition to multiplication. If we try to combine log together, we work backward. We can convert addition to multiplication. So I get log base 2 of x squared times y to the power of 4. Here I combine this expression into a single logarithm. Next example, 3 log base 5 of a minus 5 log base 5 of b. So first step, if there's a coefficient in the form, by the third law of logarithm, we can bring the coefficient back as exponent. So I get log base 5 of a to the power of 3 minus log base 5 of b to the power of 5. First step, if there's a coefficient in the form, bring coefficient back as exponent. By the third law of logarithm, bring coefficient back as exponent. Next, we have subtraction. Log base 4 of a cubed minus log base 5 of b to the power of 5. By the second law of logarithm, if we try to work backward, I can convert subtraction to division. If we try to combine log together, we work backward. Convert subtraction to division. So I get log base 5 of a cubed over b to the power of 5. Here I work backward, convert subtraction to division. Now I combine this expression as a single logarithm. Next example, half log base 7 of x plus 1/5 log base 7 of y minus 1/4 log base 7 of z. Half log base 7 of x plus 1/5 log base 7 of y minus 1/4 log base 7 of z. So, first step, if there's a coefficient in the form, by the third law of logarithm, I can bring the coefficient back as exponent. So first step, I bring half back here as exponent. I get log base 7 of x raised to a half. Here I bring 1/5 back as exponent here. I get log base 7 of y to the power of 1/5. Next, I bring 1/4 back here as exponent. I get log base 7 of z to the power of 1/4. Then, x raised to a half can be rewritten as square root of x. Y to the power of 1/5 can be written as the 5th root of y. And z to the power of 1/4 can be written as the fourth root of z. Next, I can convert addition to multiplication. Convert addition to multiplication. I get, for the first two terms, convert addition to multiplication. I get log base 7 of radical x times the fifth root of y minus log base 7 of the fourth root of z. Then I can convert subtraction to division. By the second law of logarithm, I can convert subtraction to division. For the final answer, I get log base 7 of square root of x times the fifth root of y over the fourth root of z. That's how we combine this expression into a single logarithm. Next example. One third of log base 3 of a minus half of log base 3 of b minus 1/5 of log base 3 of c. So first step, if there's a coefficient in the front, by the third law of logarithm, we bring the coefficient back here as exponent. So I get log base 3 of a raised to 1/3 minus log base 3 of b raised to a half minus log base 3 of c raised to 1/5. Next, a to a third can be written as cube root of a. B to a half can be written as square root of b. C raised to 1/5 can be written as the fifth root of c. Next, try to combine this logarithm together. Since these two terms are negative, we first of all combine negative terms together. Since these two terms are negative, we first of all try to combine this negative term together first. So I leave the first term the same. I get log base 3 of cube root of a. For these two terms, since they are both negative, pull out negative sign. I get log base 3 of radical b plus log base 3 of fifth root of c. I first of all group negative terms together. Then, by the first law of logarithm, I can convert addition to multiplication. When we combine logarithm together, we can convert addition to multiplication. So you get log base 3 of cube root of a minus log base 3 of radical b times the fifth root of c. I convert addition to multiplication. Next, I convert subtraction to division. I get log base 3 of cube root of a over square root of b times the fifth root of c. That's how we combine this expression into a single logarithm. Next example. Phi plus 3 log base 2 of x. How can we combine phi plus 3 log base 2 of x? Now, in the second term, I can bring 3 back as exponent. First of all, I can bring 3 back as exponent. I get phi plus log base 2 of x cubed. How can we combine these two terms together? In order to combine two logs together, the logs must have the same base. In order to combine logs together, the logs, these logarithms, must have the same basis. They must have the same basis. Now, how can we rewrite number phi as log base of 2? How can we rewrite number phi as log of base 2? By the third property of logarithm, x For any real number x can be written as log base a of a to the power of x. For any number x can be written as log base a of a to the power of x. So number 5 can be rewritten as log base 2 of 2 to the power of 5. The reason I choose log 2 is because the second term has log 2 here, which I use the same base. So I rewrite number 5 as log base 2 of 2 to the power of 5 by the third property of logarithm. I rewrite number 5 as log base 2 of 2 to the power of 5. Then they have the same base. I can combine two logarithms together. I get log base 2 of 2 to the power of 5 times s cubed. We convert addition to multiplication. Then we know that 2 to the power of 5 is 32. So the final answer is log base 2 of 32 times s cubed. Here we combine this expression into a single logarithm. This example, 4 minus 2 log 3 of y. How can we combine this expression together? First of all, if there's a coefficient in the form, I bring coefficient back as exponent first. So I get 4 minus log base 3 of y squared. Next, in order to combine these two expressions together, I try to rewrite number 4 using log base 3. I try to rewrite number 4 using base log of base 3. So by the third property of logarithm, number 4 can be rewritten as log base 3 of 3 to the power of 4. Number 4 can be rewritten as log base 3 of 3 to the power of 4. Then these two terms have the same log with the same base. These two terms, they both have log with the same base. Then by the second law of logarithm, we can convert subtraction to division. I get log base 3 of 3 to the power of 4 over y squared. And we know that 3 to the power of 4 is 81. I get 81 over y squared. That's how we combine this expression into a single logarithm. Next example. Combine 2 log base 5 of a minus 1/3 log base 5 of b plus a half log base 5 of c minus 3. So first step, if there's a coefficient in the form, we first of all bring coefficient back as an exponent. So I get 2, I bring 2 back first. I get log base 5 of a to the power of 2. Next, bring 1/3 back. Minus log base 5 of b to the power of 1/3. Bring half back as exponent. I get log base 5 of c to the power of half. For number 3, in order to combine these terms together, I try to rewrite number 3 using log base 5. So by the third property of logarithm, number 3 can be rewritten as log base 5 of 5 to the power of 3. By the third property of logarithm, number 3 can be written as log base 5 of 5 to the power of 3. Next, try to combine this together. Let me first of all put a negative term together. Put a positive term together and negative term together. I get log base 5 of a squared plus log base 5 of c to the half. C to the half is the same as square root of c. Minus log base 5 of b to the third. B to the power of the third is cube root of b. When we combine negative terms together, pull out negative sign, become addition in the middle. When we combine these two negative terms, I pull out negative sign, so it becomes addition. I get log base 5 of 5 cube. And we know that 5 cube is 125. 5 cube is 125. Next, combine these log together in the parentheses. I can convert addition to multiplication. I get log base 4 of a squared times square root of c. Convert addition to multiplication. Next, for the second log, for the second parenthesis, also convert addition to multiplication. I get log base 5 of cube root of b times 125. Then I can convert subtraction to division. By the second law of logarithm, I can convert subtraction to division when we combine. Convert subtraction to division. I get log base 4 of a squared times square root of c over cube root of b times 125. That's the same as 125 times cube root of b. That's how we combine this expression into a single logarithm. Next example. Combine 2 log base 7 of x minus 1/5 log base 7 of y minus 3 log base 7 of 2 of z plus 1. So try to combine this together. If there's a coefficient in the front, first of all, bring coefficient back as an exponent. So I get log base 7 of x squared minus, I bring 1/5 back here as an exponent. I get log base 7 of y to the power of 1/5. Next, I bring 3 back as exponent. I get log base 7 of z cubed. In order to combine number 1 with these 3 logs, I need to rewrite number 1 using log base 7. In order to combine number 1 with these 3 terms, I just need to rewrite number 1 using log base 7. And by the third property of logarithm, number 1 can be written as log base 7 of 7 to the power of 1. By the third property of logarithm, number 1 can be written as log base 7 of 7 to the power of 1. Then try to combine this together. Before we combine, we first of all group the positive term and the negative term together. Let's first of all group the positive term and the negative term together. I get log base 7 of x squared plus log base 7 of 7 to the power of 1 minus, I group these two negative terms together. If I pull a negative sign, it becomes addition in the middle. Log base 7 of y to the power of 1/5. Y to the power of 1/5 is the same as the 5th root of y plus log base 7 of z cubed. Next, by the first law of logarithm, I can convert addition to multiplication. When we combine log together, I can convert addition to multiplication. I get log base 7 of x squared times 7. For the second term, do the same thing. For the second parenthesis, do the same thing. When we try to combine two logarithms together, I can convert addition to multiplication. I get the 5th root of y times z cubed. Next, when we combine two logs together, I can convert subtraction to division. I get log base 7 of 7x squared on the numerator and 5th root of y on the denominator and z cubed on the denominator. That's how we combine this expression into a single logarithm. Next, let me introduce a special constant called Euler's number, E. You will learn its formal definition in your calculus class, but for now, let me give you some rough idea about what it is. Consider the graph y equal to 1 over x. In the first quadrant, the graph looks like this. It's hyperbola, but in the first quadrant it looks like this. That's a graph of y equal to 1 over x in the first quadrant. Assume 1 is here. Let x be a constant in the x-axis. That's an area under the curve from 1 to x. That's an area under the curve from 1 to x. Now here we can see that when we move x, the area changes. When x moves, the area changes. Area could be very, very small as it gets close to 1. And area could be very, very large as it goes to infinity. Since the area changes as x moves, there must be a moment then the area equal to 1. Since the area changes as x moves, since the area under the curve changes as x moves, so there must be a moment the area under the curve is 1. There must be a moment the area under the curve is 1. Since as x change, the area change. Area could be very, very small as x gets close to 1. Area could be very, very large as x go away from 1. And as we move x, there must be a moment that area under the curve is 1. When area is 1, when area under the curve is 1, this x equal to e. When area under the curve is 1, this x value here equal to e. And e is approximately 2.718 282. E is an irrational number. It's approximately 2.718 282, and so on. That's a rough idea about E, about what E is. You will learn its formal definition in your calculus class in the future. Now, this E is a special number. Next, let me introduce natural logarithm based on number E here. We use Ln of x represent the natural logarithm. Ln of x represent natural logarithm. Ln of x is the same as log of base e of x. Ln of x is the same as log base e of x. If base is e, we can write it as Ln. That's called a natural logarithm. If the base is e, for log, if the base is e, I can write it as Ln of x. That's called natural logarithm. A logarithm with base e is called natural logarithm. That's a special logarithm function. That's a special logarithmic function. Another special logarithm is called the common logarithm. Another special logarithm is called a common logarithm. For log of x, if there's no base, we assume the base is 10. That's called common logarithm. If there's no base, we assume the base is 10. If the base is e, that's called natural logarithm, write it as Ln of x. If there's no base, we assume the base is 10. That's called a common logarithm. Those are two special logarithms. And the natural logarithm is very, very useful in your calculus class. Natural logarithm is very, very useful in the future in your calculus class. Next, let me review the property of logarithms, laws of logarithms, and the change of base formulas using base e. Since this formula is true for all base a, I can rewrite this formula using base e and base 10. If I change the base to e, I have log base e of 1 equal to 0, since e to the power of 0 is 1. Log base e of e equal to 1, since e to the power of 1 is e. and so on. Log base e of e to the power of x is x. E to the power of log base e of x equal to x. Since the base is the same, they can cancel. E cancels log e. I get x here. And from the law of natural logarithm, we have log base e of xy equal to log base e of x plus log base e of y. And log base e of x over y equal to log base e of x minus log base e of y. And log base e of x to the power r, I can bring r to the front. I get r times log base e of x. And for change of base formula, since for log base a of b, I can change the base to any constant c greater than 0. C is not equal to 1. I can change the base to e. I can change the base to e. Write it as log base e of b over log base e of a. Since e is positive and e is not the same as 1, I can change the base to e. So log base a of b is the same as log base e of b over log base e of a. And similarly, I can change the base to 10. For common logarithm, I can change the base to 10. I get log base 10 of 1 equal to 0, log base 10 of 10 equal to 1, since 10 to the power of 1 is 10. 10 to the power of 0 is 1. And log base 10 of 10 to the power of x is x. 10 to the power of log base 10 of x, since the base is the same, they get cancelled. 10 cancels log 10. I get s here. And for the law of common logarithm, log base 10 of x times y equal to log base 10 of x plus log base 10 of y. And log base 10 of x over y equal to log base 10 of x minus log base 10 of y. Log base 10 of x to the power r is the same as, I can bring r to the front, it's the same as r times log base 10 of x. And then for change of base formula, I can change the base to any constant c, where c is greater than 0 and c is not equal to 1. Here, 10 is greater than 0 and 10 is not 1. I can change the base to 10. So log base a over b, log base a of b can be written as log base 10 of b over log base 10 of a. So this property is true for both natural logarithm and common logarithm. Next, let me rewrite this formula using the natural logarithm and common logarithm. Let me write the formula in a better way. For the first property, we know that log base e is the same as ln. Log base e is the same as ln. Log base e is the same as ln. So the first property can be written as ln of 1 equal to 0. The second property can be written as ln of e equal to 1, since log base e is ln. The third property can be written as ln of e to the power of x equal to x, since log base e can be written as ln. So I get ln of e to the power of x equal to x. The fourth property can be written as e to the power of ln of x equal to x, since log of base e is the same as ln. So memorize these formulas. Memorize these formulas. Those formulas are very, very useful, especially in the future in your calculus class. Those formulas are very, very useful. And similarly, I can rewrite the law of natural logarithm using ln. So the first law here can be written as ln of x times y equal to ln of x plus ln of y. Log of base e is ln. The second law of logarithm is ln of x over y equal to ln of x minus ln of y. In the third law of logarithm, we have ln of x to the power of r equal to r times ln of x. Those are the laws of natural logarithm. Memorize this formula. And from the change of base formula, log base A of B can be written as ln of B over ln of A. Log of base E is ln. Log of base E is ln. So log base A of B is equal to ln of B over ln of A. And similarly, for the common logarithm, first property, log base 10 of 1 equal to 0. We know that log base 10 is the same as log with no base. Log base 10 is the same as log with no base. So log base 10 of 1 can be written as log of 1 equal to 0. Then for the second property, log base 10 of 10 equal to 1 can be written as log of 10 equal to 1. And the third property can be written as log of 10 to the power of x equal to x. And the fourth property can be written as 10 to the power of log of x equal to x. Memorize these properties. Those are the properties of common logarithms. And same thing for the laws of common logarithms. Log base 10 is the same as log with no base. So this formula can be written as log of sy equal to log of x plus log of y. Log of x over y can be written as log of x minus log of y. If there's no base, whereas when the base is 10. And the third law here, I have log of x to the power of r equal to r times log of x. If there's no base, whereas when the base is 10. So those are the laws of common logarithm. Remember these laws. Those are the laws of common logarithm. And for the change of base formulas, log base A of B equal to log base 10 of B over log base 10 of A. We know that log base 10 is the same as log with no base. So I get log B over log A. So log base A of B can be written as log of B over log of A. Next, let me show you some examples. Use calculators to evaluate each of the following expressions and round the answers to 6 decimal places. First example, log base 2 of 3. How can we evaluate this in the calculator? We know that in many calculators, there's no function to evaluate the general logarithmic function directly. Instead, we only see the common log or natural log in many calculators. In many calculators, there's no function can evaluate general logarithmic function directly. Instead, they only have the common log and natural log in the calculator. So, how can we evaluate this using common log or natural log? So here, in order to evaluate log base 2 of 3 using common log or natural log, we must apply the change base formula. We apply the change of base formula. So in order to use the common log or natural log in the calculator, we must rewrite this logarithm using either the common log or natural log. So this can be rewritten as ln of 3 over ln of 2 or log 3 over log 2. Then in your calculator, you either do log of 3 over log of 2, ln of 3 over ln of 2, or log of 3 over log of 2. You get the same answer. And in my calculator, I get 1 0.584963. Since the general logarithmic function cannot be evaluated directly, we must change the base. Use either common log or natural log to evaluate this general logarithmic function. Next example, evaluate log base 5 of 7. Again, in general, we cannot evaluate the general logarithmic function in the calculator. We must change the base to either to common log or natural log. So log base 5 of 7 can be written as either ln of 7 over ln of 5, or common log of 7 over common log of 5. Then use calculator. In my calculator, I get 1.209062. Next example, evaluate log base 9 of 6. So this general logarithmic function can be written as ln of 6 over ln of 9, or common log of 6 over common log of 9. And in my calculator, I get 0.815465. Next example, log base 4 of 27. In order to use calculator, I will write this log as ln of 27 over ln of 4, or log of 27 over log of 4. Then use calculator. Evaluate one of them. You must get the same answer. In my calculator, I get 2.377444. So that's how we evaluate general logarithmic function in the calculator. Next, let me show how to solve equations using logarithms. Solve each of the following equations. First equation, we have 4 times 3 to the power of 2x plus 1 equal to 9. Here we try to solve x from exponent. In order to solve x from exponent, let me first of all isolate 3 to the power of 2x plus 1 first. So I can first of all subtract 1 from both sides. If I subtract 1 from both sides, I get 4 times 3 to the power of 2x plus 1 equal to 8. Next, I can divide both sides by 4. If I divide both sides by 4, I get 3 to the power of 2x plus 1 equal to 2. Now, on the left side and right side, you can see that the bases are not the same. We can match and get exponents. What I can do here is apply ln to both sides. In order to solve x from exponent, apply ln. Either apply common log or natural log on both sides. And here, let me use natural log. Apply ln on both sides. I get ln of 3 to the power of 2x plus 1 equal to ln of 2. In order to solve for x from exponent, either apply common log or natural log on both sides. Then we try to solve the equation for x. By the law of logarithm, when we have ln of x to the power of r, we can bring exponent to the front of log. When we have ln of x to the power of r, by the law of logarithms, I can bring the exponent to the front of log. So here, I can bring the exponent 2x plus 1 to the front of the natural log. I get 2x plus 1 times ln of 3 equal to ln of 2. By the law of logarithm, by the law of natural logarithm, we can bring exponent to the front. So I get 2x plus 1 times ln of 3 equal to ln of 2. Next, solve the equation for x. I can first of all distribute ln of 3. I get 2 ln of 3 times x plus ln of 3 equal to ln of 2. Next, I can move ln of 3 to the right side. I get 2 ln of 3 times x equal to ln 2 minus ln 3. Then I can divide both sides by 2 ln 3, get s by itself. So for the final answer, I get ln of 2 minus ln 3 over 2 ln 3. That's a solution for x. Next example, 3 times 5 to the power of s minus 2 minus 4 equal to a. In order to solve for x from exponent, let me first of all get 5 to the power of x minus 2 by itself first. So here I can first of all add 4 to both sides. If I add 4 to both sides, I get 3 times 5 to the power of s minus 2 equal to 12. Next, I can divide both sides by 3. If I divide both sides by 3, I get 5 to the power of s minus 2 equal to 4. So here we can see that on the left side and right side, they have the same. They don't have the same base, so it cannot match an exponent. Now, either apply common log or natural log on both sides. In order to solve x from exponent, either apply common log or natural log on both sides. In general, we apply natural log on both sides. I get ln of 5 to the power of s minus 2 equal ln of 4. So either apply common log or natural log on both sides. In order to solve for x from exponent, either apply common log or natural log on both sides. Then on the left side, by the law of logarithm, we can bring exponent to the front. I get s minus 2 times ln of 5 equal to ln of 4. By the law of logarithm, we can bring exponent to the front. Then solve the equation for x. I can first of all distribute ln of 5. I get ln of 5 times x minus 2 ln of 5 equal to ln of 4. Then I can bring this term over, bring 2 ln of 5 to the right side. I get ln of 5 times x. When I move this term over, it's negative, it becomes positive. I get ln of 4 plus 2 ln of 5. Then I can divide both sides by ln of 5. Then I can divide both sides by ln of 5. The final answer is ln of 4 plus 2 ln of 5 over ln of 5. That's a solution for x. Next example, 2 times 3 to the power of x equal to 7 to the power of x minus 1. 2 times 3 to the power of x equal to 7 to the power of x minus 1. If there are x on both sides, we directly apply, either apply common log or natural log on both sides. We apply common log or natural log on both sides directly. Then we apply the common log on both sides. Then we apply the natural log on both sides. I get ln of 2 times 3 to the power of x equal to ln of 7 to the power of x minus 1. Apply natural log on both sides directly. Then, by the law of logarithm, we can convert multiplication to addition. By the law of logarithm, ln of s times y can be written as ln of x plus ln of y. So the left side can be written as ln of 2 plus ln of 3 to the power of x. Right side stays the same, ln of 7 to the power of x minus 1. Next, by the law of logarithm, we can bring exponent to the front. By the law of logarithm, we can bring exponent to the front. Here I get ln of 2 plus x times ln of 3 equal to x minus 1 times ln of 7. Then solve the equation for x. on the right side, I can first of all distribute ln of 7. I get ln of 2 plus x ln of 3 equal to x ln of 7 minus ln of 7. Next, try to move x to the left side and ln of 2 to the right side. So here I have x ln of 3 minus x ln of 7. When I move this term from right side to left side, it's positive, I make it negative. And when I move ln of 2 from left side to the right side, it's positive, I make it negative. So I get negative ln of 2 minus ln of 7. Then on the left side, I can factor power x. On the left side, I can factor power x. If I power x, I get x times ln of 3 minus ln of 7 equal to negative ln of 2 minus ln of 7. Then, in order to get s by itself, I divide both sides by ln of 3 minus ln of 7. So the final answer is minus ln of 2 minus ln of 7 over ln of 3 minus ln of 7. That's the final answer to this equation. That's the solution to this equation. Next, 3 times 4 to the power of 2x equal to 2 times 5 to the power of s plus 3. If there are x on both left side and right side, we need to apply ln, common log or natural log on both sides directly. Let me apply natural log to both sides. I get ln of 3 times 4 to the power of 2x equal to ln of 2 times 5 to the power of s plus 3. Then, on the left side and right side, apply law of logarithms. I can convert multiplication to addition. I get ln of 3 plus ln of 4 to the power of 2x. On the right side, I get ln of 2 plus ln of 5 to the power of s plus 3. Next, bring exponent to the front. By the law of logarithm, bring exponent to the front. I have ln of 3 plus 2x times ln of 4 equal to ln of 2 plus x plus 3 times ln of 5. Bring exponent to the front. What's left is ln of 5. Next, solve the equation for x. Let me first of all distribute ln of 5. I get ln of 3 plus 2x times ln of 4 equal to ln of 2. If I distribute ln of 5, I get x ln of 5 plus 3 ln of 5. Next, move the term with x to the left side. I get 2x ln of 4 minus x ln of 5 equal to ln of 2 minus ln of 3. When I move this term over, it becomes positive term become negative. Plus 3 ln of 5. Then, on the left side, I can factor power x. On the left side, I can factor power x. If I power x, I get 2 ln of 4 minus ln of 5. Leave the right side the same. I get ln of 2 minus ln of 3 plus 3 ln of 5. Next, I can divide both sides by 2 ln of 4 minus ln of 5. So the final answer is ln of 2 minus ln of 3 plus 3 ln of 5 over 2 ln of 4 minus ln of 5. That's the solution to this equation. Next example, 2 to the power of 2x minus 3 times 2 to the power of x minus 18 equal to 0. How can we solve this equation for x? In this equation, if we apply ln to both sides, it won't work. So what we can try is, let's try a substitution. If I let u be 2 to the power of x, then how about 2 to the power of 2x? If I square both sides, u squared will be 2 to the power of x squared. Then by the law of exponent, 2 to the power of x squared is 2 to the power of 2x. So 2 to the power of 2x is u squared. And 2 to the power of x is u. If I substitute, I have a quadratic equation here. Then I can solve this equation by factoring. I have u minus 6 times u plus 3 equal to 0. Here I find two numbers. They multiply to be negative 18 and they add to be negative 3. I get u minus 6 times u plus 3 equal to 0. Then solve each of the equations individually. I get u minus 6 equal to 0 and u plus 3 equal to 0. Solve the equation for u. I get u equal to 6 and u equal to negative 3. In the first equation, I add 6 to both sides. In the second equation, I subtract 3 from both sides. So I get u equal to 6 and u equal to negative 3. Which means 2 to the power of x equal to 6. Since u is 2 to the power of x. And 2 to the power of x equal to negative 3. We know that 2 is a positive number. Positive number raised to any power won't be negative. So this answer is rejected. That's impossible. 2 is a positive number. Positive number raised to any power won't be negative. So this answer is rejected. For the other answer, 2 to the power of x equals 6. How can we solve the equation for x? For this equation here, I can apply ln to both sides. If I apply ln to both sides, I get ln of 2 to the power of x equal to ln of 6. Then, by the law of logarithm, I can bring exponent to the front. I get x times ln of 2 equal to ln of 6. Next, I can divide both sides by ln of 2. I get s equal to ln of 6 over ln of 2. That's a solution to this equation. Next example. 5 to the power of 2x minus 2 times 5 to the power of x minus a equal to 0. How can we solve this equation for x? If I directly apply ln to both sides, it won't work. So what I can try some substitution. If I let u be 5 to the power of x, then u squared will be 5 to the power of x squared. That means u squared is 5 to the power of 2x by the law of exponent. 5 to the power of x to the power of 2 is 5 to the power of 2x. So u squared is 5 to the power of 2x. Next, let's substitute. I get u squared minus 2u minus a equal to 0. Then solve the equation by factoring. I can put u on each parenthesis. Then find two numbers that they multiply to be negative a and add to be negative 2. We can try negative 4 and positive 2. When we multiply, we get negative a. When we add, we get negative 2. Then solve each equation individually. I get u minus 4 equal to 0 and u plus 2 equal to 0. If I solve the first equation, I add 4 to both sides, so u equal to 4. If I solve the second equation, I subtract 2 from both sides, so I get u equal to negative 2. Here, u is 5 to the power of x, so I get 5 to the power of x equal to 4, and 5 to the power of x equal to negative 2. Since 4 is a positive number raised to any power won't be negative. So this answer is impossible. It must be rejected. This is impossible. Positive number raised to any power won't be negative. So there's no solution here. For the other equation, I can apply ln on both sides. I get ln of 5 to the power of x equal to ln of 4. Then, by the law of logarithm, I can bring x to the front. By the law of logarithm, I can bring exponent to the front. I get x times ln of 5 equal to ln of 4. Next, I can divide both sides by ln of 5. So the final answer is s equal to ln of 4 over ln of 5. That's the final answer to this equation. Next example. 7 to the power of 2x minus 5 times 7 to the power of x plus 6 equal to 0. How can we solve this equation for x? We can try to do some substitution. The u equal to 7 to the power of x. Then u squared will be 7 to the power of x squared, which means u squared is 7 to the power of 2x. By the law of exponent, 7 to the power of x to the power of 2 is 7 to the power of 2x. Then substitute. I get u squared minus 5 times u plus 6 equal to 0. This is a quadratic equation. I can try to solve an equation by factoring. I write u on each parenthesis, then find two numbers that they multiply to be positive 6, add to be negative 5. The only possibility is negative 2 and negative 3. Negative 2 times negative 3 is positive 6, and negative 2 plus negative 3 is negative 5. Next, set each equation equal to 0. I get u minus 2 equal to 0, and u minus 3 equal to 0. Solve each equation for u. I get u equal to 2, and u equal to 3. In the first equation, I add 2 to both sides. In the second equation, I add 3 to both sides. So I get u equal to 2, and u equal to 3. Here, u is 7 to the power of x. So plug in. U here is 7 to the power of x. I get 7 to the power of x equal to 2. And 7 to the power of x equal to 3. Next, in the first equation, I apply ln on both sides. I get ln of 7 to the power of x equal to ln of 2. Then, by the law of logarithm, I can bring exponent to the front. I get x times ln of 7 equal to ln of 2. Then I can divide both sides by ln of 7. I get s equal to ln of 2 over ln of 7. That's one solution. For the other solution, I can also do the same thing. Apply ln to both sides. I get ln to the power of 7 to the power of x equal to ln of 3. Then, by the law of logarithm, I can bring exponent to the front. I get x times ln of 7 equal to ln of 3. Then I can divide both sides by ln of 7. I get s equal to ln of 3 over ln of 7. So we got two solutions for this equation. Next example. 3 to the power of 2x plus 7 times 3 to the power of x plus 12 equal to 0. In order to solve this equation, let's make substitution. Let me let u equal to 3 to the power of x. Let u equal to 3 to the power of x. Then u squared will be 3 to the power of x squared. Then by the law of exponent, 3 to the power of x squared is 3 to the power of 2x. Then substitute. I get u squared plus 7u plus 12 equal to 0. Then I can solve the equation by factoring. I try to find two numbers that they multiply to be 12, add to be 7. The only possibility is 3 and 4. Then set each factor equal to 0. I get u plus 3 equal to 0 and u plus 4 equal to 0. Solve each equation for x for u. In the first equation, I can subtract 3 from both sides. I get u equal to negative 3. In the second equation, I can subtract 4 from both sides. I get u equal to negative 4. Then substitute. Replace u with 3 to the power of x. Replace u with 3 to the power of x. I get 3 to the power of x equal to negative 3. And 3 to the power of x equal to negative 4. Since 3 is a positive number raised to any power will be negative. So there's no solution here. This answer is rejected. Also, 3 is a positive number. 3 raised to any power will be negative. So this answer is also rejected. If both answers are rejected, there are no solutions. If both answers are rejected, there are no solutions. So this equation has no solutions. This equation has no solutions. Next example. Log base 2 of x plus 3 equal to 4. How can we solve this equation for x? Log base 2 of x plus 3 equal to 4. It means, by its definition, it means 2 to the power of 4 equal to x plus 3. By definition of logarithm, it means 2 to the power of 4 equal to x plus 3. And then solve the equation for x. We know that 2 to the power of 4 is 16. Then I can subtract 3 from both sides. I get s equal to 13. Now, if the equation contains log, we must check the answer. If the equation contains log, we must check the answer. Make sure the number in the parentheses must be positive. For log a of what's in the parentheses, this number must always be positive. If this number is negative, that's undefined. So the number in the parentheses here must always be positive. So let's check. If I plug in 13, 13 plus 3 is positive. So this answer is valid. 13 plus 3 is positive. So this answer is valid. If we get negative answer in the parentheses, then this answer must be rejected. Next example. 3 times log base 5 of 2x minus 1 equal to 5. If the equation contains log, let's isolate log first. So I can first of all add 1 to both sides. I get 3 log base 5 of 2x minus 1 equal to 6. Next, I can divide both sides by 3. I get log base 5 of 2x minus 1 equal to 2. Then, by the definition of logarithm, we know that 5 to the power of 2 equal to 2x minus 1. This expression means 5 to the power of 2 equal to 2x minus 1. So we have 5 to the power of 2 equal to 2x minus 1. And 5 squared is 25. Next, I can add 1 to both sides. I get 26 equal to 2 times x. Then I can divide both sides by 2. I get s equal to 13. Now, if the equation contains log, we must always check the answer. Make sure what's in the parentheses is positive. Log cannot take negative numbers. If we have log of negative number, the answer must be rejected. Log of negative number is always undefined. Let's plug in 13. If I plug in 13, I get 2 times 13. That's 26. 26 minus 1 is 25, which is positive. So this answer is valid. The answer is 13. This answer is valid. If we plug in, we get some negative number in the parentheses, then this answer must be rejected. Next example. log base 2 of x plus 3, x plus 2, plus log base 2 of x minus 4 equal to 4. How can we solve this equation for x? Log base 2 of x plus 2 plus log base 2 of x minus 4 equal to 4. So, if there are two logarithms with the same base, by the law of logarithms, we can combine two log together. By law of logarithms, when we combine, I change addition to multiplication. I get log base 2 of x plus 2 times s minus 4 equal to 4. I combine these two log into a single logarithm by changing addition to multiplication. That's the first law of logarithm. Then, by the definition of logarithm, log base 2 of this equal to 4. That means 2 to the power of 4 equal to this expression. By the definition of logarithm, that means 2 to the power of 4 equal to this expression. So 2 to the power of 4 equal to s plus 2 times s minus 4. Then simplify. 2 to the power of 4 is 16. If I distribute, I get s squared minus 4x plus 2x minus a. Next, I can combine like terms. If I combine like terms, I get negative 2x. Negative 4x plus 2x is negative 2x. Then I can subtract 16 from both sides. If I subtract 16 from both sides, I get 0 and negative 24. If I subtract 16 from both sides, negative a minus 16 is negative 24. Then I can solve the equation by factoring. Here I get x minus 6 times s plus 4. I find two numbers, then they multiply to be negative 24 and add to be negative 2, which is negative 6 and positive 4. Then set each factor equal to 0. Set each factor equal to 0. I get s minus 6 equal to 0 and s plus 4 equal to 0. Then solve the equation for x. In the first equation, I can add 6 to both sides. I get s equal to 6. In the second equation, I can subtract 4 from both sides. I get s equal to negative 4. Next, if the equation contains log, we must always check the answer. Let's check 6 first. If I plug in 6, 6 plus 2 is positive. 6 minus 4 is also positive. So 6 is valid. If I plug in negative 4, negative 4 plus 2 is negative 2. Log base 2 cannot take negative numbers. So this answer is invalid. It must be rejected. Log base 2 cannot take negative numbers. Log of any base cannot take negative numbers. So this answer must be rejected. The only solution is s equal to 6. This answer is rejected. Next example. Log of x minus a plus log of s minus 5 equal to 1. This is common log. If a log with no base, that's a common log. If there are two logs, we try to combine these two logs together as a single logarithm. By the law of logarithm, by the first law of logarithm, log of x plus log of y can be written as log of x times y. I can convert addition to multiplication. So I get log of s minus a times s minus 5 equal to 1. And for common log, if there's no base, whereas when the base is 10. For common log, if there's no base, whereas when the base is 10. So, by definition of logarithm, it means 10 to the power of 1 equal to this expression. Log base 10 of this expression equal to 1, it means 10 to the power of 1 equal to this expression. So by the definition of logarithm, it means 10 to the power of 1 equal to s minus a times s minus 5. Then simplify both sides. On the left side, 10 to the power of 1 is 10. On the right side, if I distribute x, I get s squared minus 5x minus ax plus 40. Then simplify. I get s squared negative 5 plus negative a. Negative 5x minus ax is negative 13x. Combine like terms. Negative 5 plus negative a is negative 13. Then I can subtract 10 from both sides. If I subtract 10 from both sides, I get positive 30 here. Then this is a quadratic equation. I can solve an equation by factoring. Put x on the parentheses. Find two numbers. Let me multiply to be 30, add to be negative 13. We can try negative 3 and negative 10. Then set each equation equal to 0. Set both factors equal to 0. I get s minus 3 equal to 0 and s minus 10 equal to 0. Then solve each equation individually. In the first equation, I get s3 to both sides. I get s equal to 3. In the second equation, I can add 10 to both sides. I get s equal to 10. Then, if an equation contains log, we must check the answer. If I plug in 3 minus a is negative 5. And we know logarithmic function cannot take negative numbers here. So 3 must be rejected. Logarithmic function cannot take negative numbers. So 3 must be rejected. If I plug in 10 minus a is positive, so that's valid. 10 minus 5 is also positive, so 10 is valid. The only solution is 10. 3 is rejected, so 10 is the solution for this equation. 3 is rejected. Next example. Log base 2 of 2x plus 6 minus log base 2 of s minus 1 equal to 2. If an equation contains two logs, we try to combine these two logarithms into one logarithm as a single logarithm. So, by the second law of logarithm, we can convert subtraction to division. When we convert subtraction to division. So I get log base 2 of 2x plus 6 over s minus 1 equal to 2. So in the equation, if there are two logs with the same base, let's combine these two logs together first. Then, by the definition of logarithm, log base 2 of this expression equal to 2. That means 2 to the power of 2 equal to this expression. So, by the definition of logarithm, 2 to the power of 2 equal to this expression. 2x plus 6 over s minus 1. Then solve the equation for x. Here, 2 squared is 4. 4 can be rewritten as 4 over 1 equal to 2x plus 6 over s minus 1. Then I can cross multiply. If I cross multiply, I get 4 times s minus 1 equal to 2x plus 6 cross multiply. Then I can distribute 4. If I distribute 4, I get 4x minus 4 equal to 2x plus 6. Next, I can subtract 2x from both sides. I get 2x minus 4 equal to 6. Then I can add 4 to both sides. I get 2s equal to 10. Then I can divide both sides by 2. I get s equal to 5. Now, be very careful. If the equation contains log, we must always check the answer. If I plug in 5, 2 times 5 is 10. 10 plus 6 is 16. That's positive, so this is valid. If I plug in 5 here, 5 minus 1 is 4. 4 is also positive, so that's also valid. So, x equal to 5. That's a solution to this equation. This solution is valid. That's a solution to this equation. Next example. Log base 5 of s plus 2 minus log base 5 of 2s minus 2 equal to negative 1. How can we solve this equation for x? In an equation, if it contains two logs with the same base, we can combine these two logs together first. By the second law of logarithm, we can convert subtraction to division when we combine. So we get log base 5 of s plus 2 over 2s minus 2 equal to -1. Then log base 5 of this expression equal to -1. By definition of logarithm, it means 5 to the power of -1 equal to this expression. It means 5 to the power of -1 equal to this expression, s plus 2 over 2s minus 2. Then on the left side, 5 to the power of -1 is 1 over 5 equal to s plus 2 times 2s minus 2. Then I can cross multiply. If I cross multiply, I get 2x minus 2 equal to 5 times s plus 2. If I cross multiply, I get 2s minus 2 equal to 5 times s plus 2. Then I can solve an equation for x. Distribute 5 first. I get 2x minus 2 equal to 5x plus 10. Then I can subtract 5x from both sides. I get negative 3x minus 2 equal to 10. Then I can add 2 to both sides. I get negative 3x equal to 12. Then I can divide both sides by negative 3. I get s equal to -4. Now, if the equation contains log, we must check the answer. Make sure also in the parentheses is positive. Log cannot take negative numbers. If I plug in -4 plus 2 is -2, which is negative. Since log base 5 cannot take negative numbers here, this answer is rejected. If I plug in -4, I get -4 plus 2, which is negative. Log base 5 cannot take negative numbers. So this answer is invalid. It must be rejected. If there's only one solution and it's rejected, that means there are no solutions. If there's only one solution and it's rejected, that means there are no solutions.